Yes, good evening. So, welcome to another a new presentation on control system subject. So, in today's presentation, I would like to explain you that the steady state error. Steady state error. By the way, this is lecture number 36. Okay, so today we will see steady state error. Steady state error. So this is denoted by E suffix SS. This is another important topic in control system. What is a steady state error? Okay, so what is the importance of this? Okay, so steady state error is nothing but the error signal or the difference signal between the output to the input. Okay, I will explain you. So I think, have you remembered that in our first presentation we have seen that any control system in general is represented by this block diagram. I think we have seen in our very present first, I mean, presentation. So any control system with feedback loop is represented by this. So this is your input R of S. This is your output C of S. This is gain actually. This is the gain. This is the feedback. We are giving, we are feeding back to this input. Okay, this is always plus. The input is always plus. Whereas this is, let us say, negative feedback. So part of the output, C of S is the output, part of the output we are feeding back through this feedback. The gain of the feedback is H of S, and this is we are giving again to this summer point. So here if you observe this summer point or summing point, the input R of S as well as this H of S is uh, going to this point. Okay, so therefore here C of S, part of the output is nothing but C of S. From means C of S we are giving like this, so it comes like this, means this C of S. Okay, this is what the C of S only giving back. Now what is the output here after H of S? It is C of S into H of S, that is the product, no? So this is the output after this H of S. Okay, this much quantity we are giving here. Now this is the difference signal. Here the output of this error signal is called as E of S, that is error signal. E of S is nothing but here, E of S is nothing but your error signal or difference signal. So this is nothing but E of S is nothing but the output which is coming out from this summer point. E of S is equal to your R of S. Okay, this is going now, this is coming inward, positive sign, therefore R of S is positive always, minus this one, C of S into H of S, C of S into H of S, that is what, this one, C of S into your H of S. Let us consider this as equation number 1. Consider this as equation number 1 from this expression, from this block diagram. Okay, and again now write another expression from here. C of s is equal to gain into input. C of s is equal to G of s into E of s. Is it not? C of s is equal to, I will remove this, I will erase otherwise. So this is first expression, E of s expression, and again I will write another expression for C of s. So your C of s is equal to G of s into E of s. G of s into E of s. This is your second expression. Clear? So C of s is nothing but gain into input. So I am considering this block only. The output of this block is your C of s. So C of s is equal to gain into input. So G of s into input. Input is nothing but E of s. Okay. So this is the first expression. This is the second expression. Now what we will do is that, so substitute equation 2 in equation 1 for C of s. So you have C of s in equation number 1. So at the place of C of s, you substitute C of s is equal to G of s into E of s into here. Means substitute 2 into 1. Clear? So now I will erase this diagram. So here I will bring one expression. That's why I want to bring one expression. So by substituting, you write like this. By substituting equation 2 in equation 1. So then if you substitute this equation 2 into 1, then this 1 becomes, from 1 means you write like this, means from first equation, means from here, how it will becomes, E of s is equal to R of s minus, what is your C of s? Nothing but this one, G of s into E of s into H of s. Clear? So here in place of C of s, you write, substitute G of s into E of s. Okay, so substituted. Then and further from this implies, so on the right side G of s into E of s into H of s is there. On the left side E of s is there. If you bring this quantity to the left side, okay, so E of s is there, so this total quantity bring to the left side, then E of s and again here E of s, take E of s as common here, then E of s 1, this minus comes here, then plus, no, so 1 plus E of s you have taken as common, then what remains, G of s into H of s is equal to, what will be there on the right side, only R of s you will have. From this, what is E of s expression? E of s is equal to, bring this total 1 plus G of s into H of s onto the right side, then it goes to denominator part R of s by 1 plus G of s into H of s. This is the expression for your E of s basically. This is the error signal. This is the error signal, E of s only. So E of s is equal to your R of s by 1 plus G of s into H of s. This is the expression. This is the error signal. Now, what is the steady state error? What is the steady state error? So, steady state error is nothing but the value of the error signal. It is, the steady state error is nothing but it is the value of the error signal E of t. This is the Laplace transformation. E of s is nothing but Laplace transformation. So if you take the inverse Laplace transformation, then it will comes into E of t. Clear? So I will erase here and I will explain you. E of s is nothing but Laplace transformation form basically. So E of s is the So here E of s is the Laplace transformation form. So I want E of t. So E of t is nothing but, if I want E of t, then you must apply inverse Laplace transformation to the E of s. So for this E of s, if you apply the inverse Laplace transformation, then that becomes E of t, error signal in time domain. This is the error signal in S domain, means frequency domain, you can say. Normally S is nothing but your frequency. S equal to j omega actually, that we will see in other applications. But whereas as far as our control system is concerned, just you remember E of S, that much only. Frequency concept will not come here. Okay, so S domain and then time domain. So E of t. So what is the steady state error? Steady state error is nothing but, it is the value of steady state error. Steady state error. What is steady state error? It is the value of, it is the value of error signal. Error error signal as t tends to infinite. It is the value of error signal as t tends to infinite, as limit t tends to infinite. That is the steady state error. Okay, the value of E of t at t tends to infinite is nothing but error signal. Means that is represented by the, it is represented by steady state error is represented by E suffix ESS. So therefore ESS is equal to limit t tends to infinite E of t. Clear? This is what the definition. Clear? So steady state error means, E means error, steady state. Therefore steady state error is equal to limit t tends to infinite E of t. E of t means the error signal as t tends to infinite. So the value of E of t at t is equal to infinite gives the steady state error. Clear? Okay, now so so we have seen ESS now. So next what we will see. So we have seen this is the definition of steady state error. Okay, now see that steady state, I mean, there are some error constants. Error constants are there, error constants. So normally there are three types of important error constants are there. These constants can be studied. These constant can be seen by applying various standard input signals to the control system. Okay, so basically there are three types of input signals: unit step input signal, unit ramp input signal, unit parabolic input signal. So unit step signal, unit ramp input signal, unit parabolic input signal. For these three types of input signals, what are the different steady state errors? Or otherwise you can say the error constants. What are the error constants will come. Therefore, remember that now we have seen that ESS is nothing but, what is this? Limit t tends to infinite E of t. Clear? This is what we have seen. So here there is one important theorem of Laplace transformation, that is what the final value theorem. According to the final value theorem of, according to final value theorem, according to final value theorem of Laplace transformation, okay, according to the final value theorem of Laplace transformation, what is the final value theorem? Say for example, f of t is any given function, then Laplace transformation of f of t can be given as f of s. Clear? So time domain converted into s domain after the application of Laplace transformation. Then according to final value theorem means that limit t tends to infinite f of t is equal to limit s tends to 0 s into f of s. This is the final value theorem of Laplace transformation. Clear? Very important theorem it is. There are two types of theorems basically, initial value theorem and final value theorem. Here as t tends to infinite, we are considering that is nothing but final value theorem. If t tends to 0, that is initial value theorem. But as far as this is concerned, our error, steady state error is concerned, the limitation is going from t tends to infinite. That's why we are considering the final value theorem. According to the final value theorem, if the function f of t is reaching to t tends to infinite, if this time tends to infinite, correspondingly in the s domain, the s value tends to 0. If t tends to infinite in time domain, correspondingly in s domain, the s tends to 0 and it comes like this, s into f of s. S into f of s. So this is the very important formula, final value theorem. You apply this theorem to this steady state error. Then here your function is e of t. So consider your f of t is nothing but e of t. Then if e of t is your function, then according to the final value theorem of the Laplace transformation, let us see what will happen if e of t is our function. If e of t is our error signal, if you apply the final value theorem to this, then that means that limit t tends to infinite e of t is equal to limit s tends to 0 s into e of s. Clear? Clear? This is what, according to the final value theorem of the Laplace transformation to this error signal e of t. So e of t is the given function now, error function or error signal. Then according to final value theorem, Laplace transformation limit t tends to infinite, e of t is equal to s tends to 0 s into e of s. So just now we have seen that what is e of s basically. E of s is equal to what? Just now we have from the block diagram, just you refer previously what we have seen that. So e of s is equal to, we have seen the expression e of s is equal to r of s by, we have derived now from those two equations by substituting the second equation to 1. We brought an equation that e of s is equal to r of s by 1 plus g of s into h of s. Clear? So substitute this e of s value here. Then what is the steady state error? Then what is the steady state error? If you substitute that, if you substitute this, then your steady state error is equal to limit. Okay, limit. What is this? Either you can write t tends to infinite, e of t is equal to limit s tends to 0 s into e of s. Basically e of s is nothing but this one, r of s by 1 plus g of s into h of s. This is the final definition. This is the final definition. Therefore steady state error is equal to, you must remember, limit s tends to 0 s into r of s by 1 plus g of s into h of s. This formula you must remember always. ESS is equal to this one, limit s tends to 0 s into r of s by 1 plus g of s into h of s. Clear? So, okay. Then what is r of s? R of s is nothing but input, the s domain, the Laplace transformation of r of t. Okay, r of t. R of t is nothing but your input. Clear? Therefore, what you should remember is that the steady state error ESS is equal to limit s tends to 0 s into r of s by 1 plus g of s into h of s. This definition you must remember for steady state error. Now, as just now I explained you that there are three different types of inputs normally we can apply in control system. The first one is unit step input signal. What is unit step input signal? Unit step input signal. So for unit step is nothing but what is the how this unit step signal is defined? The unit step signal is defined as normally it is denoted by u of t. U of t is equal to 1 for t is greater than or equal to 0 and it is 0 for t is less than 0. That is the definition of a unit step signal. This is the unit step input signal. Okay, now if you this is what, so you can write this as r of t also as far as our subject is concerned. You can consider because r of s is there, therefore you can treat u of t as in general the unit step is denoted by u of t in general, but for the sake of our subject here, because u of t can be considered as r of t. Now r of s is nothing but the Laplace transformation of r of t, means that if you apply the Laplace transformation to this r of t, means Laplace transformation of your, what is r of t? R of t is nothing but u of t. U of t is nothing but 1. So LT of 1. What is LT of 1? It is 1 by s. Laplace transformation of 1 is 1 by s. Clear? So this is again from the definition of the Laplace transformation. Okay, that you can see in your mathematical that thing. Basically that is a simple definition. Actually there is nothing big this thing actually. So for your quick reference I can explain that also. So if f of t is any given function, then Laplace transformation of f of t can be given as Laplace transformation of f of t can be given as, the definition is like this: 0 to infinite e power minus s into t f of t dt. This is the Laplace transformation definition of f of t. So here in this definition substitute 0 to infinite e power minus s into t. What is f of t? F of t is nothing but your r of t input. What is that value? 1, no? It is 1 into dt. Integrate this. You calculate the integration of that function. So that gives us what this gives actually. So L of t of f of t we have just now written, that is nothing but your r of s actually. So we are calculating by the way r of s is equal to this one, that is 0 to infinite e power minus st into 1 if you multiply these two, e power minus st only into dt. This is equal to, further if you integrate, if you calculate this integration part, then what we will have? E power integral of e power minus st, e power minus st. Again with respect to t you will have minus s in denominator part. Clear? 0 to infinite. So take minus 1 by s as come outside, because minus is there, 1 by s is there, take out e power minus s into t. So this implies minus 1 by s e power minus st. In t place substitute upper limit infinite once, means e power minus s into infinite minus lower limit minus e power minus s into 0 lower limit. So what it will comes? Minus 1 by s e power minus infinity is s into infinity infinity minus infinity, so 0 minus S into 0, 0, 0, e power 0 is 1. So it is minus 1. Minus into minus, plus 1. Therefore, obviously, the answer is 1 by S. Clear? Your R of S is 1 by S. Therefore, R of S is 1 by S. This is what the Laplace transformation of your unit step function. So substitute this R of S value here, then your ESS becomes ESS is equal to limit S tends to 0, S tends to 0, S into what is R of S? It is 1 by S from this by 1 plus G of S into H of S. Means S will cancels out, then limit S tends to 0, then 1 by 1 plus G of S into H of S. Okay, clear? So S tends to 0. This is what. Now apply this limit to these terms. So here S term is not there. Therefore, furtherly this can also be written as ESS is equal to, say here, further ESS is equal to from here 1 by 1 plus limit S tends to 0, this one, G of S into H of S. Clear? You apply this limit to these terms because 1 is constant, however, therefore 1 will be there because no S term in that, therefore 1 is as it is it will be there. Then, so this limit will be applied to here. Therefore, this is called limit S tends to 0, G of S into this part. This is called, what is this? Kp, positional error constant. So means that it is called ESS is equal to 1 by 1 plus, normally this can be written as Kp, where Kp is equal to limit S tends to 0, G of S into H of S. Kp is called positional error constant. This is one error constant. This is called error constant. Therefore, 1 by 1 plus Kp is the steady state error for the unit step input. Clear? This is clear. So this is what. Therefore, what is ESS? So for the ESS is equal to 1 by 1 plus Kp. So in this form, they will ask you in examinations, GATE examination or UPSC IES examinations. So for unit step input, they will give you some C of S by R of S equal to some function they will give problem. And for for unit step input, you need to find out the steady state error. So for steady state error, what you have to calculate very simply, if you apply limit S tends to 0, G of S, H of S, then position error constant will be obtained. If you substitute the position error constant in this formula, then you simplify and get the value. That is what ESS, steady state error, for that. Similarly, if you apply the unit ramp signal second, this is the first formula. Remember this is the very important. And coming to the second one, second input, if you consider unit, the second one is unit ramp input signal. What is unit ramp input signal? Normally here the unit ramp signal is equal to R of t is equal to t. This is for t is greater than or equal to 0, and it is 0 for t is less than 0. That is the definition of a unit ramp. It is nothing but it looks like this. This is t, time. So this will be ramp signal actually. As the time goes on increases 1, 2, 3, 4 like that, then obviously correspondingly the amplitude also comes. If time is 1 second, one unit amplitude will be increases. If the time is 2 seconds, correspondingly amplitude will be 2 units. If 3, 3, 4, 4. If you join all these points, corresponding points, it comes a slope. It is like it is nothing but a ramp. So ramp signal, that is the definition. So for this, if you apply the Laplace transformation, then R of t becomes as R of s. Okay. Then if you take the Laplace transformation of t, then it becomes 1 by s square. I think for proof of this, you may please go through your mathematical this thing, because it takes time here to derive this, because it's already mathematical. From mathematical point of view, you already know this how it is. So for ramp signal, that Laplace transformation of R of s is equal to 1 by s square. Therefore, if you apply this R of s value in ESS, so the steady state error is equal to limit s tends to 0. What is that formula then? S into R of s by 1 plus G of s into H of s. This is what our definition, no? This is what our R of E of s is. So here in R of s place, 1 by s square is substituted. So 1 by s square, 1 by s square if you substitute, s into s will be cancelled out. 1 by s will be there. That 1 by s, so that s you bring to the denominator, then s, okay, s will be multiplied here. Means s plus s into G of s into H of s will come. Clear? So I will write for you. So here E of ss is equal to limit s tends to 0. It is yes, R of s is nothing but your 1 by s square by 1 plus G of s into H of s. Clear? So this s will be cancelled out. Then limit s tends to 0. It is 1 by s in general. 1 plus G of s into H of s. No? So what I am doing? So you bring this s to denominator 1 by s, na? The s comes here. Then obviously limit s tends to 0. You can write like this also. S plus s into G of s into H of s. Clear? You can write like that also. Now apply the limit. So limit s tends to 0. You apply the limitation to this. As s tends to 0 means s will become 0, no? S will become 0. Then what remains actually? For this second term, you need to apply the limit. Means 1 by limit s tends to 0 s into G of s into H of s. This will be your E of s. This is called. So here this limit s into G of s term is there, no? This is called k suffix v, velocity error constant. Velocity error constant. Clear? So the limit, so here limit s tends to 0 s into G of s into H of s. This particular, this is called as your kv. Remember that. What is kv? Kv is nothing but velocity error constant. Velocity error constant. Okay, velocity error constant. Therefore, for the unit ramp input, if they ask you to find out steady state error, first of all, you need to calculate the velocity error constant. If you calculate that and simply 1 by limit, so 1 by kv, 1 by that constant value gives E of ss value. That's all. That's all. Clear? So therefore ESS, finally how we can write? ESS is equal to 1 by kv. That's all. Velocity error constant. So if you know the velocity error constant, if you do the reciprocal of that 1 by, okay, kv, that gives your velocity error constant. So for the unit ramp input, what kind of constant we will get? It is velocity error constant. And for unit step, it is positional error constant, kp. This is okay. And similarly, the third one is unit parabolic input. Unit parabolic. Unit parabolic input signal. Unit parabolic input signal. That is nothing but unit parabolic input signal. Nothing but R of t is equal to t square by 2. That is the definition actually. If you take R of t as input, R of t is equal to t square by 2. Same for t is greater than or equal to 0, and this is equal to 0 for t is less than 0. This is the definition. And for this is R of t basically. If you apply the Laplace transformation for this input, then R of t becomes as R of s. Then t square by 2 becomes as 1 by what will come? 1 by s cube basically. 1 by s cube. So previously R for ramp signal, R of t is equal to 1 by s square. Here it comes 1 by s cube. 1 by s cube basically. Now if you substitute this 1 by s cube in that steady state error formula, then what you will get, it is simple. So the steady state error, clear, the steady state error ESS is equal to limit, what is that? S tends to 0, your R S into, so S into R of S by 1 plus G of S into H of S, no? This is equal to limit S tends to 0, S into what is R of S? 1 by S cube by 1 plus G of S into H of S. Here S will be cancelled out, then it is limit S tends to 0, 1 by S square by 1 plus G of S into H of S. And further this can be written as limit S tends to 0, 1 by S square plus S square into G of S into H of S. Clear? Now apply limit value here as we have applied in previous section for unit ramp. If you apply S tends to 0, then this part again becomes 0 here. Then only it will remains. Then obviously what it will come? ESS is equal to limit limit directly I will write directly. ESS is equal to, it is 1 by S square term will become 0. Then obviously limit S tends to 0. This is S square into G of S into H of S. That's all. This further can be written as K suffix A. Here where Ka is equal to this entire part, limit S tends to 0, S square into G of S into H of S is called your K. What is K? K is nothing but your acceleration error constant. Acceleration error constant. Therefore, what we have obtained basically, so we have seen the steady state error definition, and we have brought the definition for error steady state error, and from there we have applied 3 types of inputs, means unit step input, unit ramp input, unit parabolic input. So for unit step input, what is the steady state error? And what is for a unit ramp input, what is the steady state error? For unit parabolic input, what is the steady state error? So these are the formulas basically. Okay, so in the next presentation we will see some examples or some previous questions which have been asked in previous question papers, right? So I think you have enjoyed it, and I hope that you understood well. Okay, so definitely if you can understood, or if you have any clarifications, definitely don't forget to comment on my channel. And okay, so if you would like to my channel, you please like it and you can share to your friends. And if you have uh, any clarifications, you please comment, and we will try to give you the better this thing, right? Thank you and all.